All right. Good afternoon, class. Happy Thursday. So, I guess sort of for right now, so the homework assignment is due tomorrow. So hopefully that's coming along nicely. That's the one where you have to basically show the tree after every insert and deletion for your B tree or 2-3 tree, sorry. And basically, as was mentioned on Discord, yes, so every part builds off of each other. So for parts A, B, C, and D for those questions, whatever you get in part A, you want to use that updated tree to insert whatever is in part B. So that's that. So nothing too tricky on that one. Just sort of follow the notes on this. I had it where I only remove and insert, I only remove from the leaf level, which will make it a little bit easier than removing from in a interior node level. So you have to move pointers around and so forth. So it makes it a bit simpler, but yeah, nothing really too bad on that assignment. So I guess I'll go ahead now just continue from last time's content, which we just started talking about graph theory in this course. Let's go ahead and begin a screen share. Here we are. All right, so graph theory. So basically, the main applications, I guess, network, also a map, could also be another use of a graph, and I guess any problems that can be reduced to a graph problem. But anyway, let's skip past that. So a graph basically is just going to be a set of vertices and a set of edges, and edges really connect vertices together. And of course, we have undirected graphs where the edges, they don't have a direction, which means that A can go to B and B can go back to A as well. For directed graphs, we draw these arrows, which sort of denote that we only can go one direction. So A goes to B and B does not go back to A unless we have another directed edge that has B with the arrow going to A. So that's sort of how this works. And we can sort of see it's going to be our set V and set E, just like that. So we can kind of represent a graph kind of using set theory, set notation, essentially. So we have a set of nodes or vertices and a set of edges. Each edge is a pair of two nodes, which will just tell you which two nodes will connect to each other with an edge. So I guess now what I'll do is go over how do we actually store a graph if we were to actually program this. We're not going to really go over code in this class, but I'll just sort of go over how you'd be able to code this. There's two main ways to store a graph in memory. We have adjacency list and adjacency matrix. So I'll go ahead and I'll just first draw an example graph once again, and then I'll just go ahead and show both versions of these and explain which one is the better one to use in certain circumstances. And then we'll go over kind of our first kind of graph traversal algorithm. So let's go ahead and put a line here to just sort of go over our ways of storing a graph into memory. So I'm going to first just create a graph, and I'll just use a directed graph for this example. So I'm going to have several sort of nodes. Let's go ahead and just sort of insert these here. So let's first draw these nodes, and then we'll go ahead and we'll just put we'll label them and put the edges in later. So I'll go ahead and I'll just call these, I guess this will be A, B, C, D, E, F, and I'm going to just use, this will be a directed graph, so each sort of connection, we're going to basically just have sort of a direction arrow. I guess I'll have also B will go back to A as well. That, I guess maybe A would go to D as well. D goes to E. Let's see what else we have here. I'll just connect the rest of these. So B would go to C, or E would go to C, sorry. I guess I'll have also B also go to C as well. And then C goes to G. That. And let me see what else. I'll have also C goes back to B also. So we kind of that's the same picture right there. Yeah, I have to let you get this into shape. C, we go back to B. And let's go ahead and draw a few more of these. There we go. So we have a graph right there. So we have our set of nodes, we have our edges connecting them. So I'm going to first go over the first method, which will be adjacency matrix. So let's see how many nodes you have. 1, 2, 3, 4, 5, 6, 7. So we have 7 by 7 matrix. Then I'll zoom out afterwards once I first put this matrix here. 2, 3, 6, and 7. Wider like this. I think that should be good enough. So we have a 7 by 7 matrix. Like that. So anyway, I'm going to label these with the letters. So A, B, C, D, E, F, B, and we'll also label it over here as well. So you might have seen this already when you did sort of graph theory in CS 302. So basically in this example, we're going to do is we're going to pretty much mark all of our connections. So for right now, in this main diagonal, I'm going to go ahead and leave this kind of blank for right now because really, it's really up to you how you want to set that up. But really, we're going to have it where we're going to see which two edges or which two nodes, sorry, are connected to each other. So A does go to B. So I'm going to mark this as T for true. And then let's go ahead and go to the rest of A's neighbors. So A also goes to D as well, with A true. And the rest, I'm going to mark them as false. So false implying that there is no edge connecting those two nodes. So A only goes to B and to D, and that's it. So let's go ahead and do the rest of these. So B also goes to A, so let's just work this one out. B does go to C as well. It does not go to D. It goes to E. I think that's it for B. It only has those three. So okay. And the rest will mark them as false. So false implying once again that there is no connection between those two nodes. There's no edge from B to D or B to F or B to G. Now for C, C has two neighbors. It goes to B and G. So this and the rest would be false. When I see you only have two outgoing neighbors, I believe. Now I'll fill the rest of these out. D has a neighbor that goes to E and F. So D goes to E and F directly with one sort of edge. And as to the rest of these, so E only goes just to C, I believe, looking at that. Oops. That's true. And the rest, I'll mark these as false. Just like that. And then I guess for here we have F goes to E, and I guess it just goes to E from what I can see there. F only goes to E. And the rest will just be false. And then the last one, we're going to have for G, and I think that only goes just to F, I believe. So I'm going to go ahead and put the true over there. And the rest will be false. So if you read this matrix, sort of the row index is going to be our source node and the column is destination. So we're saying, does A go to D? So if this right here contains a true, that means A does go to D. That is a false, that means there is no edge that goes from A to that sort of node E. So that's sort of how we look at, how we read this structure. This will be an adjacency matrix for the given graph. So if you were to write actual code to traverse and do work on a graph, you're going to have to use this as your input. You're going to have this, not input, but it's going to be your structure you're going to use to navigate through your graph. So pretty simple. So adjacency matrix. And the other approach we have is adjacency list. So I'll also go over that as well. So we're going to, it's going to be an array of linked lists, which typically in CS 302, my students always Always very happy to see that. Yeah, they always like that. One, two, three, stay. So shape here, try it. Box. One, two, three, four, five, six, and seven. Perfect. So we're going to have an array of linked lists over here. And of course, the indices will just be the nodes. So if you use numbers, we can easily map it to an element. If you're using letters or a string as our vertex names, then possibly a hash map would be used to map that name to an index in an array. And then you would actually store a linked list for the value field for that hash map. But of course, that's more of a 302 thing. So just now, just sort of magically, we'll know that A is the first index, B is the second index, and so forth. So right now, what's going to happen is, well, we have these neighbors. So A goes to, let's see, it goes to B and D. So I'm going to go ahead and just sort of create two nodes. Try to use actually, try to make it look a little nicer. So I'll use the actual sort of feature. So A goes to B and A goes to D. And we can assume we have a linked list. Nice. Like that. So we sort of have this array of linked lists, and we just sort of have these nodes that sort of tell us the neighbors of a node. So this does not really imply that B does go to D. This only implies that A has a neighbor that goes to B, and A also goes to D. We just sort of store the neighbors of every single node in this structure. So for B, we have three neighbors. You have A, C, and E. So I guess ACE. Have these three. Oops, this came out a little good. Better. A, C, and E in that linked list. Let's go through the rest of these. So C goes to B and G. Create these two nodes over here. That. And then for D, it has two neighbors E and F. So I'll put these two nodes over here as well. E and F. Just like that. And E only goes to one element, goes to C. Nothing too bad here, I don't think so far. And F goes to E. So we'll just go ahead and I'll put this over here. And then G goes to F. This will be our adjacency list. So you kind of read this where all you have to do is go to an index in this array of linked lists and then traverse each node to see what are the neighbors. So if I want to see, is there an edge from C to G? Well, I have to go to index C in this list and traverse to those two neighbors. So we have B and we have G. So then we know we have a neighbor that we have an edge that goes from C to G. So if you were to code this, you have to maintain the structure and you have to be able to cycle through each node's neighbors list or edge list. So you can go ahead and do basic traversals through a graph. So then, okay, so, and also, I guess this main diagonal here for the adjacency matrix, it's up to you what you want to put here. So you can put like, a true, you can put a true over there because, A is already at A, or also some graphs, there actually will be an edge that goes to itself. So for example, you can have a graph like this. I'll just erase this quickly, but I'll put this here for a second. You can have a graph where it goes like this, where A goes to itself. Not so common, but you can have a graph like that. So it's up to you how you want to have this set up, where you want to have a true, which implies that must be an edge from A to itself, or a false, implying there is no edge to A to itself. But typically, you don't have to worry about that because if you're at node A, you're already there. So you don't have to worry about if there's an edge that goes to itself because you're already there. So there's no need to worry about that. But sometimes that could be a factor in certain situations. So Okay, so I guess which one's a better one to use? And the answer to that question is that, well, they're both going to work. You can store a graph either way and be able to code simple traversals using either approach. So really it depends on if you want to save memory or not. So we have two types of graphs. I'm going to just write some notes over here. So we essentially have, whoops, I'll use consistent here. We have sparse graphs. We also have dense graphs. These two over here. And they sort of speak for themselves. So sparse kind of means empty, not so many. So sparse graph really means that there aren't, isn't, there aren't, isn't too many. I guess I'll say isn't. There isn't too many, isn't too many edges in the graph. Okay, it's kind of very layman's terms, but the more technical term is the following. So we have this, which is, I guess, E is going to be our set of edges, and that's going to be a set theory. So that's the cardinality of E. So not the absolute value of E, but the cardinality of E. It's going to be this. So basically, a sparse graph means that we're going to have the amount of edges is going to be linearly related to the amount of vertices. So if you have so basically, it could be 5v or 10v or whatever, but it's going to be some linear amount with respect to the amount of vertices in your graph. So remember, v is your set of vertices, e is your set of edges. So we're going to have the following sort of relation. So we're going to have basically a linear relation between the edges and the vertices. Now, for a dense graph, which speaks for itself, means we're going to have a lot of edges. There are many edges in graph. So we want to go ahead and figure out what's the max number of edges we can possibly have. So let's go ahead and first do that. So max edges, let's go over for a directed graph. Well, this is a case where we have a node or vertex, and it has an edge to every single vertex in your graph, except to itself, I suppose. So you have one vertex that goes to every other vertex in your graph, so all of them except to itself. So then you can sort of count this by saying for each vertex v, you're going to have exactly v minus 1 edges. So clearly, in this situation, it's going to be equals O of v squared. Now, if we have an undirected graph, well, let's go ahead and do that as well. So max edges for an undirected graph. Well, in this case, same idea. We're going to have v. We'll apply it to v minus 1, but divided by 2 because, well, in this example, if you have an edge from A to B and B to A, it's going to be just one single edge. Whereas for a directed graph, you actually have to have an edge from A to B and B to A. So we divide it by 2 because we're not going to have two. So if you have an edge between two nodes, only one edge is going to sort of be, so that one edge will equal two edges in a sense, because you don't have to have two separate edges because that one edge can go both ways for undirected graph. So basically you have this scenario, which either way, this is still going to be quadratic. So either way, it's going to be the cardinality of v is going to be O of cardinality of v squared. So basically, for dense graph, it's going to have a lot of edges, which really means we're going to have quadratic amount of edges with respect to the number of vertices. In dense graph, it's going to be linear. So basically we're going to have no more than v squared because you don't need more than v squared. Otherwise, you have redundant. You have multiple edges that goes between two nodes, which makes no sense anymore. So you're never going to have more than v squared, but you could have just v if you have a sparse graph. So how does this actually relate back to adjacency list and matrix? Well, if you have a sparse graph, storing graph using um, adjacency list saves memory. So let's go to back up to the example we had our graph above. So looking at this graph over here. So we create a 7 by 7 matrix. So we have 49 element matrix. And for this graph, as we can see, this is a rather sparse kind of graph. You don't have so many edges in this graph. But for adjacency matrix, we actually still have to allocate space just to store these falses, which really is a waste of space. Why even have all that extra content? We don't need that really. So for adjacency list, we only maintain these truths basically. So looking at the adjacency list over here, all the extra, let's say for example, A goes to F. There is no edge made F, so we don't even maintain it in this list. So we don't have to reserve all these extra spots just to store a false because really we only need that. We only have to maintain really just um, these elements that which actually denote their edges in our graph. So we don't have to really maintain A goes to E, A goes to F because that's useless. Who cares? Because we can just easily not include that in our set of edges. So that's why it's better to use this list version if you have a sparse graph. Now for a dense graph, however, it doesn't really matter which one we use really. So for dense graph, so if you have dense graph, then um, so either way, so either um, adjacency list or adjacency matrix um, sort of uses um, the same amount of memory, or relatively speaking. Because of course each node has a pointer stores in it as well, so it does waste a little more memory, but overall it's about the same amount. So it doesn't really matter which one you use in that case. So possibly a matrix is a better idea because it is easier to navigate through a matrix versus using a list because you can actually, if you want to verify if there's edge from node 0 to node A to B, you can just automatically go to row A, column B, and check right away. In constant time, you can verify if an edge exists between these two nodes. Whereas for a list, you have to traverse that linked list. So I guess maybe a matrix would be a better idea because either way, you're not going to be able to save memory either way. So I guess you might as well use adjacency matrix situation. So that's sort of how we actually um, store a graph into memory. So I'm not going to really refer to this anymore because I go over more theoretical parts, but I guess I'll kind of paraphrase or just sort of mention how the code actually would work for or how the pseudocode would work for our different graph traversal techniques. So our first main sort of graph traversal is going to be depth first search, which you also might have seen this in CS302. So this might be a little bit of a review, but that's okay because we're going to go over other contents as well. But let's first go over our basic graph traversal. Let's first go over depth first search. Sometimes a DFS. Now, otherwise called that first search is really a traversal type for a graph. It's just a traversal. It's a simple graph traversal. So basically, it's a recursive function. It's very equivalent to using, it's almost like a pre-order. So you've done tree traversals in 302. It's really a pre-order that's applied onto a graph. That's sort of the idea. And the way it works is we're going to go as deep as when we traverse sort of through our graph. Um, basically, we go as deep as possible in the graph. And sort of once we hit a dead end, as we reach a dead end, we go back to the previous vertex and try a different neighbor. So that's how DFS works. All we do is we arrive at a node. We simply just pick a neighbor, pick any neighbor, just pick one. And we go to that node. And we just keep on doing this until we can't go any further. Hit a dead end, we back up, and then we try a different sort of path. That's really about all we're going to do. So also, you can construct, so sort of you can construct a DFS forest, the graph, which really just sort of maintains, it sort of just maintains sort of the paths taken by DFS. So, I mean, I guess it's in the books. I guess I'll go over how to construct the forest as well. But typically, you're not going to really need to directly use it, but it's in the books. So I guess I'll try to go with that book just so there's some consistency, I suppose, with this course. So let's go ahead. And I have this sort of from the book, the actual pseudocode for I guess, depth first search. So I'm going to go ahead and just sort of refer to that, I guess. I do have the code from like 302, but I'll use the book, the MIT books sort of code just so it's a bit more formal, I guess. So we're going to have our function DFS. So I'll write this over here, pseudocode for DFS or depth first traversal, or it's search, but really, doesn't have to be a search. I don't know why they call it DFS because it's really a depth first traverse. So we're just traversing in this type of depth first order, I guess. But they call it depth first search. Right? That's what it's called. So sure, let's call it that here. So DFS, and we're going to pass in a graph. So G is going to be your graph, and G is going to be most likely some adjacency matrix or list. But we'll just go ahead and just sort of consider G as just like this graph, which has a set of vertices and a set of edges. But if you were to code this, you would pass in some adjacency list or matrix into this function. Okay, so I guess in this book, they use sort of ways of coloring a node as white, gray, or black. So I guess I might use sort of, maybe I'll use white, then I'll use blue and red, I suppose. So that way we can see all the colors here. But that's sort of how they have it in the book. So I'll just sort of be consistent with that. So we first have DFS. What's going to happen is we're going to have this loop. So for each vertex u in our set of vertices, we're going to go ahead and set u dot color is going to be set to white, which means that we haven't really visited this edge, or sorry, this node just yet. And then this is the weird notation used in the book, but I'll say u dot pi. So each edge will have it's going to be like a struct, I guess you can say. So the color will tell you if it's been visited or not. So in the book, they use white, gray, and black. I'll use white, blue, and red. I'll use actually instead. So the idea is that this pi is going to be a predecessor element. So we're trying to see what is the predecessor of u, basically. I'll put this here just so we have this, just to help us. I'll use green to draw this, write this out. So u dot pi is the predecessor node of u. So we want to maintain this back point. We want to know what node so basically we want to know what node we came from to get to this node u. That's what that u dot pi is supposed to be. So that's in the book is pi, so I'll just be consistent with that just in case. If in case I should read that book, which I'm guessing you probably won't because that book is really not a fun book to read. It's a really complicated book actually, but that's the only book we have. And of course the UC book is nicer, but there's less content in that. So that's kind of the unfortunate thing there. Then we're going to have our time variable equal to 0. So we're going to label each node. So we're going to have these timestamps when we first arrived at the node and when we process the node, which I don't think it's super important to have this, but it's in the book, and I guess it can be useful. I mean, you can have some homework questions I can sort of use based on that time factor, so sure. And now we're going to actually run our depth first search traversal. We're going to say for each vertex, in V, in this set of vertices. So then if dot color equals white, which means that it hasn't been processed just yet, then we'll go ahead and we'll call this function dfs visit, and we're going to pass in the whole graph and pass in u, which is going to be the node we're going to explore in this traversal. That's going to be our DFS function, which is basically this function just sets up our graph, basically, or sets up our traversal, sorry. Then DFS visit is going to actually be our recursive function that's going to perform this traversal. I'll put this over here. So we're going to have DFS visit. We're going to pass in G, and we're going to pass in some vertex U. And then we're going to first increment our time plus 1. Maybe keep this more pseudocode, not C++ code, I guess. And then we're going to set, so U dot, I don't know why I use D actually, but I'll just put this here. So we're going to set use discovery time. So we're going to set when we discovered this node U in our traversal. So every iteration of DFS, we increment our time counter by 1. So it's going to always tell us when we actually reached that node. And then we're going to set U dot color. We're going to set it to gray, which I'm going to use blue. So in the book, they use the word gray, but gray will be blue for us. So gray means that we arrived at this node. It's currently in our DFS path. We haven't processed it just yet. It's still kind of being processed, if you will. And then we're going to go ahead and have a loop within our DFS traversals. I'll put a little space here between these two. So for each for each vertex B um, in use neighbors list, we're going to basically set, so if v dot color equals 8, so which means we haven't discovered this node just yet, then I want to go ahead and do the following. So I'm going to first do this. I'm going to say v dot pi equals u. So we're going to say that v's predecessor is going to be u. So we just simply store, so we're going to explore node v. And I want to set the predecessor of v. So u was the node that we came from to get to the node v. And of course, we're going to now call DFS visit. We're going to pass in, of course, the graph G and then the node V. We're going to explore that node. And of course, afterwards, when we're done, once we finish this loop, then U dot color, we're going to set this to be black, but you're going to use red over here, like that. And then we're going to set the time, increment this by 1 because now we process this node. So time equals time plus 1. And we're going to set U dot F v time. We're going to set U's sort of final time or the process time. So that's going to be DFS, written in this sort of sophisticated MIT pseudocode approach. That's going to be our DFS function. So DFS visit is going to basically just perform this recursive function, recursive traversal. And that loop inside of DFS, so this loop right here, so I'll just sort of mark this, that loop right there exists because you could have a disconnected graph or an unconnected graph, sorry. So certain nodes are not reachable through a node. So you want to make sure that you go ahead and restart DFS on one of our nodes that's not marked visited or not marked white. So that way we can, of course, continue and restart DFS on a new node. If in case from a starting node, you're not able to reach every possible node in your graph, which is a possibility. Now we'll do an example where I think this example will be able to go through every single node, but if not, we can easily go ahead and call DFS on this new node. Let's go ahead and sort of draw this graph over here and try to trace out that first search on this graph. First time traversing it using this MIT's sort of algorithms. Let's see if I hope I don't mess this up too bad. Here's our graph will be given. It's going to just create this graph right here. Let's see. So I'll use. Okay, so we'll go ahead and use sort of a directed graph just because. Circle here. I think that's good enough. Now just use letters to denote these. So A, B, C, D, E, and H. Now go ahead and just sort of, go ahead and put all the edges here. Oh, so draw this as well. Let's see, I'll try this one. B goes to C, C goes to G, C goes to D as well. C also will go to F, F will go to G and to H. E will go to H as well, and I guess H will go to G. I think it's a good enough graph. But there we go. We have it. We have our graph right there. So I'm going to label each of these nodes. I'm going to use a dot, so this will imply that these are all not visited. So I guess in the book they use they label this as white, which means you have not visited this just yet. I'm going to put a slash over here. So we're going to maintain the discovery time and the how should we call it? Discovery time and the final time. So this will be, I'll use a slash here. So I'll have a number slash. So we'll have a discovered time and our final time. I'll put these over here as well. Every single node. And also I'm going to put pi above. Right now it's going to be all zero, so we're going to sort of store each node's predecessor as well. So put it like this maybe. This one here, I guess. Yeah, sure. Put this one over here. This last one over here. Okay, so let's go ahead and first work this out. So in our code that we're given, I'll put time over here just so we can always have our time value. And it's going to initially just be, I guess it'll be essentially 1, or we first set it to 0. But then what's going to happen is when we first call our function, we're going to set the time to be just simply 1. So right now, we'll choose A as our first node. That's going to be our first node in our traversal. So what we're going to do right now is the following. So first enter this node A, we increment time by 1, and u.d is going to be 1. So for A, the discovery time is going to be just 1 at this point. And then we're going to sort of color this sort of node to be gray, which I'll use blue to do this. So blue implies that we haven't sort of, we just got here, we discovered it, but we haven't finished processing it just yet. And then we're going to just basically now go ahead and traverse to every one of A's neighbors. So for A, we have 2 neighbors, B and E. I'll choose B as my first neighbor. So that means right now we're going to go ahead and call DFS on B. So in our for each loop, we first choose V. It's going to be that node B, and we're going to set so we're going to go ahead and just basically set the pi value to be A. So for B dot pi contains A, which means that B's predecessor is going to be A. So we came from A to get to B. And then we're going to go ahead and recursively call DFS on that node B. So now we enter this, and then of course, we enter this node B. And the first thing we do in this recursive function is increment time by 1. Make time, so I guess I'll just put it as 2. So time will now be 2 because whenever we call DFS visit, we're going to basically call increment time by 1. So we're going to set B's discovery time to be 2. And then we're going to color this node to be gray, or in this case, we'll color it to be just blue. This will be, I guess, our version of gray, which means that this node has been discovered and it's no longer going to be, we're not going to ever come back to this node again. So we discovered it, but it's not processed yet, but we've seen this, this node. So now we're going to do is go through all of B's neighbors. So I guess for B, we have 2 neighbors. So I'll choose C in this case. So we have to do a loop which will go through all of B's neighbors. So we would have C and F. It would essentially be in our adjacency list. It would have those 2 nodes in the list for B's neighbors list. So I'll choose C just because. What will happen is we're going to set C's pi value to be B, which tells us that C, so we went through B to get to C. So we just have to store these predecessor sort of values. So we know we came from B to get to C. And then we're going to go ahead and call DFS visit on this node. So the first thing we do is we enter this function call, increment time by 1 to make it 3. And we're going to set this node's discovery time to be 3. And we're going to mark this node as gray, which I'll use blue as a way to mark it as gray, just like that. And then what happens is we have to go through all of C's neighbors. So C has several neighbors. We have D, F, and G. So I'm going to pick D as where I'm going to go to. So we have to go through, we got to pick a neighbor basically. So I'm going to go ahead and pick D. So what happens is we're going to go ahead and take D's pi value and set it to C, which means that we're telling it that we came from C to get to B. So D dot pi equals C means C is a predecessor of D in this that first search traversal. So basically here what we're going to do is we're going to now go to this node D, and the first thing we do, we enter a new function call, increment our time by 1 according to how our pseudocode is written. We increment our time by 1, and then we're going to basically set discovery time to be 4. Just like that. And then what's going to happen is we're going to basically go through all of all of D's neighbors. And of course, I have to first set this to gray. Next thing we have to do, my mistake, set it to gray. And then we have to go ahead and go through all of D's neighbors. And we're done with this because there's no neighbors, so that loop will run pretty quickly. We'll just never even run that loop. So we're done. We have all neighbors processed. So now, after that loop is done in that DFS visit function, we're going to mark this node as processed. So I guess red is going to denote that it's processing. We mark this node as red. And then we're going to basically increment time by 1 again. That's what we do in that function. And then we're going to set this sort of D dot final to be 5. So for this node, discovery time is 4, and the process time will be 5. So we process this node at time 5. Okay, so we have to go ahead and return back to the previous function. So the last node we were processing was at node C, because from C went to D, we returned back. So now we have to go ahead and pick a different neighbor for C, because we only can finish C, we only can process C completely once we've processed all of its neighbors. So right now for C, we only processed D, we didn't process F or G yet. So let's go ahead and process F next. So the first thing we'll do is we're going to update F's pi value to be B, which implies that F's predecessor, made a mistake, it was be C, my mistake. So F's predecessor is going to be C. So we came from C to get to this node F. Okay, so now we enter this function sort of body, and the first thing we do is increment time by 1, make it 6, and we're going to set the discovery time of this to be 6, and we're going to mark this node as gray, or in this case blue. Blue means it's been discovered it so far. So now what's going to happen is we have to go through all of F's neighbors. So we marked it as gray. Now we have to go and find every neighbor of F. So F has several neighbors. Well, we have E, we have H, and we have G. I'll choose E. So in that case, in this example, we're going to take E's dot pi is going to be F, which we're just going to mark that E's predecessor is going to be F in this traversal. And we're going to call DFS visits on this node. The first thing we do is we call a function, we increment time by 1, make it 7, and we're going to set 7 to its discovery time. Mark this node as gray, or in this case blue. And we have to go through all of their neighbors. So for E, we have 2 neighbors, A and H. So we look at A, and A's been marked gray. So A's color is going to be gray or blue, which means that we've already seen this node. So we don't really want to actually, go there. So we're going to not go to node A. So we'll get the next neighbor of E, which will be H. H is colored white, which means we haven't seen H yet. So we can go ahead and call DFS visit on that node. So we're going to basically now just go ahead and set this H's pi to be E. Means that we went from node E to get to this node H. Then we're going to enter this function body. Then we're going to increment this by 1 to make time 8. And I'll put this over here. So discovery time will be 8. And then we're going to mark it as gray. So we've already seen this node. All right. So now we have to look at all of H's neighbors. So for H, well, we only have one neighbor, which will be G, and G is marked white, so we haven't been there yet. So we're going to go ahead and go to that node G. So the first thing we'll do is we'll set this pi value to be H, implying that we came from H to get to this node G. We're going to go ahead and enter this function call, and we're going to set the time to be 9 because we first increment time by 1 when we first enter DFS visit, and we're going to set the G's dot discovery to be 9, mark it as gray, just like that, or blue. And now we're going to go through all of G's neighbors, and G has no neighbors, so I guess we're done. So that loop that's inside that DFS visit function, we're going to basically just escape that loop and then color this as black, or in this case I'll use red, like that. And then we're going to pretty much increment time by 1, make it 10, and set the time to 10. So that's going to be its final time. So we have those two numbers. The first is the discovery time. The second will be our sort of final time. And then we return back. So we have to we maintain all of these functions in a recursive call stack. So we know the last function that we called was we had DFS visit, and H was the node we were currently processing. So we first picked a neighbor for H. And we picked G, and there was no more neighbors left to choose. So now we have to continue that DFS visit call after that loop is done. And we're going to set this sort of node's sort of color to black, or in this case to red, which means we've processed that node. And then we're going to set time to be time plus 1, make it 11, and we're going to assign 11 over there, which is the time we finished processing this node. So we discovered it at time 8, and at time 11, that timestamp is when we processed the node completely. So anyway, now we're going to go back to the previous function call. So we last called it where we called DFS visit, and we were calling it on E because we came from E to get to H. So we basically go to E. Okay, so now we have to resume E. We have to pick a different neighbor for E. And what happened was, well, there's no other neighbor because we tried A and it's marked, gray or blue, so we can't go there. We went to H, so now we're done with E officially. So that loop that goes to all of E's neighbors, we're done. We escape that loop, and we're going to set this color to be black, or in this case to red. Increment time by 1 to make it 12. And we're going to set the final time to be 12. And now we're done with this node. We go back to the previous node. So previous nodes we were on F. So with F, well, we actually went from F, we picked neighbor E. So for F, we still have to choose 2 more neighbors because we have that loop that will go through all the neighbors of F. So F's neighbor is E, the next neighbor is going to be H. And we see that H is not marked white, which means we've already discovered it, so we're going to ignore that, skip that. The next neighbor of F is going to be G, and we've already seen G as well, so that's it. We tried all of F's neighbors, and now we're done with F. So now we're going to have to mark F as black, or in this case as red. Increment the time by 1 to make it, I guess, 13. And we're going to assign 13 to F's final time. Then we go back to the previous function. We go back to C. That was the last node that we were currently working on. So from C, we picked F, and we went and recursively called DFS visit on F. So from C, well, we tried D, we tried F. The other neighbor of C would be G. But we already processed G earlier, so we can't go there, and there's no more neighbors left for C. So now we're going to go ahead and mark this node as now processed. So we can mark it black, or in this case red. Increment this time by 1, make it 14, and assign 14 C's final time. Then we go back to the previous function call. We're going to call, we went back, we had DFS where we were DFS visit function and we were on B. So from B, we chose C back then as our neighbor. So now we have to pick a different neighbor for B. Let's try F. That's the other neighbor, right? But we've already processed F because F is not colored white, so we can't do anything there. So we're going to go to the next neighbor of B, and there is no other neighbor, so we're done with that inner loop, that loop inside that DFS visit function. We're going to now set this as, mark it as black, which means we processed this node, increment that time by 1, make it 15, and then we're going to set this to be 15 for its final time. Then we go back to the previous node. We go back to node A. So from A, well, we last time left off, we were in that for loop, and we tried to pick B as our neighbor. And after we're done with that, we have to pick a different neighbor. So we had to go through all of A's neighbors. So we only chose B so far, way back when we first called DFS A. And now the next neighbor of A would be E, but we see that E's already been marked as is not white, so it's been discovered already, so nothing we can do there. Now there's no more neighbors left for A, so you have to go ahead and mark this as black or as red. Increment the time by 1, hit 16. Set this to be the final time is 16. And then we go back to that function DFS. So what would happen is if there was some nodes in this graph that was not marked red after this, we would go ahead and we would restart DFS on that new node. Now in this case, every node was reachable from A, so we didn't have to do that, but that loop in that DFS function is designed just to call DFS. If let's say we had a case like this where we had say with R and then T and then Z like this, let's say, and it was like that, and R was not reachable from A, we'd go ahead and we would restart. We'd restart DFS on R, T, or Z, and then traverse that as well. But in this example, every node was reachable from node A, so we didn't have to worry about that. So that's how we actually do this. So we just basically we have to make sure we know if a node is visited or not. So really, just using a 0, 1 is good enough, but I guess MIT book, they want to go more in depth with this and use sort of not seen, processing, and then processed, essentially. So also these numbers over here kind of give us an idea of when we processed a node and how long it took, when we discovered node, sorry, and how long it took for us to process it. So the first numbers tells us, well, we first visited this node, then this node, then this one, then this one, and this. So it kind of gives the order in which we processed the nodes. And that second number really tells us when we actually officially, sorry, when we discovered. The second number tells us when we processed the node, which could be useful. It tells us a little bit about the node, whether it has dead ends in there. It's I guess, there are sort of text or sort of conceptual questions you can ask on a homework or an exam based on these numbers. So I might, maybe on a homework assignment, sort of based on these numbers, prove or disprove the following sort of statement. So if let's say these discovered numbers and final numbers are different, or based on what they are, we can make sort of conclusions based on that. But I guess I'll leave that sort of open and we'll have homework questions that does cover that. Anyway, so let's say we can of course show the forest, I guess. So sure, I'll show the forest or the tree for DFS traversal tree. So basically these pi values kind of tell us the story for this. So basically I can go ahead, I'm going to draw the DFS tree over here. So I guess I'm going to just choose a number with the biggest sort of discovery time. So I guess G will be right there. So to create this tree, we first pick the node that has the largest discovery time, which we can see at G clearly has the largest because it has 9 for discovery time. Then we construct the tree by taking G's predecessor as H. So we go ahead and put H over here. That. And then the predecessor of H will be E. And the predecessor of E is going to be F. Hopefully I don't want a space over here. And then F's predecessor is going to be C. We have to move this picture down maybe in a second. And then C's predecessor is going to be B. Okay, I better move this down a little bit because I'm running out of space. Going to be B. And then B's predecessor is going to be A. And A has no predecessors. So then we didn't incorporate every single node just yet. So we haven't looked at let's see, we have A, B, C. So we haven't looked at D just yet. So D, its predecessor is going to be C. Not the best sort of tree, but there we are. That's our DFS tree, I believe. So A, B, C, D, E, F, G. So that's going to be our tree essentially. It kind of tells us the paths that are taken, really. So this is kind of the path that DFS sort of took. So you could have more complicated sort of DFS trees, but that was just one. So tree really tells us exactly how this DFS really traversed this structure. So for DFS tree, typically, it'll not be a very nicely kind of full tree. It's going to be a very kind of very narrow tree is how it's going to look like. Because typically we just keep taking an edge until you can finally can't go any further. We back up and try other edges. So really, it's going to be a very narrow tree for the most part. Now, I could have, chosen different edges in our path earlier and have a different possible DFS tree. So there's more than one possible tree. It depends on what order you traversed your graph, or what edges, or sorry, what nodes you chose when you were going through the neighbors of a particular node when you were traversing, when you were processing a node in that first order. So that's sort of an example of worked out DFS. So I guess maybe on a homework assignment, I could put a question like this on there. Nothing too bad, and show me the tree given this. So there's more than one possible answer. So I guess for the grader, it might take a little bit of effort to see because, of course, I could have chosen E first. Or I could have chosen A and B. I could have chosen F instead of C. So based on what sort of edge I choose, I would get a different possible set of numbers and different possible DFS tree. So it's kind of the bummer there. So I guess some more notes I'll cover with DFS is going to be classification of edges, which is also in the book. So it's mostly designed so you can have, test questions and homework questions on this. So just, I guess, some nifty proofs, nifty questions you can ask. So let's go over the following. Classification edges. So we're going to have tree edges. So tree edges is going to be edges in the DFS forest or tree. Now, there's no forest here because from our starting node A, everything was reachable. But of course, if I would have had a graph where it was disconnected, then we could have a forest of possible DFS trees. So in this case, it's a forest of only one tree, really. So anyway, an edge B that was first discovered exploring the graph. So basically, every edge we have here in this DFS tree or DFS forest, I'll say tree slash forest. So all of these edges right there, that's going to be our tree edges. So anyway, there's that. So let's look at the rest of our different types of edges we can have. We have also back edges. There's going to be edges. Is UV connecting, vertex, U to an ancestor, B in the DFS tree. So here's a very fancy definition of this, but really all a back edge is an edge that goes back to an existing sort of, how shall we say, a node in your graph. So let me go ahead and sort of outline this for you right here. So in this example, we'll be an example of back edge over here. So let's take a look, see if we can find one. So this would be an example of a back edge in this particular example, because A is an ancestor of E, because you go from A goes to B, B goes to F goes to E. So you can very easily determine if E is an ancestor by following. So E's predecessor is F, F's predecessor is going to be C, C's will be B, B is going to be A. So we can tell that for E, actually, F, C, B, and A, all three of those nodes are ancestors. They sort of are their predecessors. So if you have an edge that goes to a node that's an ancestor, that means that's a back edge. And a back edge really determines a cycle. If a back edge is present in a graph, when you do depth first search, that implies a cycle in the graph. So I guess maybe you can kind of explain why that is. Maybe for a homework assignment, explain if a back edge is present, why is there a cycle? Or is there a cycle present? Of course, when can you discover, when are you able to determine if an edge is a back edge? So using the code given, or this pseudocode, when can you determine that you found a back edge? So that's kind of little sort of little preview of what you could have for homework potential. Let's go over forward edges next. Forward edges. It's going to be non-tree edges, non-tree edges. Which edges will be just going to be U and B, obviously. It's going to be connecting U to, let's see, ancestor. V and S. I think it's really, yes, I copy it from the book directly, but really a forward edge is going to be essentially this, though. So let me just go ahead and do an example of that. So we can think of a forward edge. Okay, so I guess B going to F, this would be a forward edge. For this example right here, B goes to C, C goes to F, but there's also this alternative sort of edge that goes straight from B to F. It's kind of like skipping the line, basically. So look at this example. In our graph, we have an edge that goes from B to F, like that. So B and F are both going to be in this, they're both going to be in this DFS tree. But we have an edge that goes kind of to one of its ancestors, if you will. Not ancestors, actually, I guess B's ancestor of F, but it goes to it like that. So a back edge would be something like this. So for example, like I guess E going to A, that would be a back edge. I'm going to put this here. Because This edge is not in our DFS tree, but this edge exists in our graph. And it goes back to an element that it goes back to one of our ancestors. And a forward edge looks like this. Hit the word forward here if I can. Oh, good enough. Forward edge is like this. There's more than one back edge possibly, but that's just an example. I'll be back in a forward edge. And then we'll have our last one. Is a cross edges. Sounds fancy. Cross edges. Okay, so it's going to be all other. So you can say edges that go between vertices in DFS tree as long as one vertex is not ancestor. No, it's other. They also go between vertices different as trees. So basically it's really is not a forward or a back edge basically. So it's just sort of it's an edge that's not in your DFS tree and they're not really, it's not a back or forward, so they're not really ancestors of each other. So let's see if I can find one in this graph over here. So let's see here, I'm going to erase this part. So it's so in this example, let's see, so F is there actually from F to D? Ah, darn, there isn't. So I guess there isn't an example. Well, let's see. So if let's say F to D had an edge, if let's say we had an edge from F to D like this, if we had this, then this would be a cross edge. So this is just if we happen to have one like this, I guess if you will. I put that there just right there because I guess this one didn't have an example to think of because actually, no, there isn't any other example. So if I were to have an edge like that, then that's a cross edge because basically it's between two. So this edge would not be in our DFS tree or forest, and it connects these two nodes, and they're not ancestors. F and D are not ancestors of each other in this traversal because for D, the ancestor will be C, B, and A. Same thing for F, but F and D are not ancestors of each other, basically. So depth first search really the very simple way how it works. All we do is we add a node and we pick an edge. We just keep picking until we can't go any further. We back up and we try a different approach. So it's just like if you have a fork in the road, let's say, you just pick one direction. That's it. You can't go any further. You back up to the last fork in the road and try a different fork in the road. That's really how depth first search works. So we'll do some examples next time, some more examples involving depth first search, and I'll write some more notes on these, but I think we're almost done with class for today, so that'll be it for right now. So take care, you guys. Stay safe. Thanks for watching. Have an awesome weekend. Have a great Halloween, and I will see you guys next week, Tuesday.